Hello, students. I hope you are doing well. So this is the video that would help you get ready for test number 2. So I'll briefly go over the problems on your practice test number 2 in calculus, which is your Math 213. All right, so let's get started as we go over those problems. So you may want to take out and perhaps print out, at least take a look at practice test number 2. And that has a dozen questions. All right, so I'll be sharing the screen and I will not be giving you detailed explanations because those are provided in your answer key, but I will be just talking about and commenting on those problems. All right, so let's get started. Okay, so this is the practice test number 2, which covers sections 2.6, 2.7, and then 3.1, 3.2, 3.3, and 3.4. And I hope you will understand that it's not about every single topic in these sections, but basically the important stuff in this section, all right? And what's important and what's not. Well, as you look at these problems, you'll have a sense of what is important and what is not so important in these sections. Okay, so let's start with number 1. Actually, numbers 1 through 5 all have to do with surfaces in R3. Okay, so let's go over these briefly. Number 1, sketch and identify the surface. X squared plus y squared plus z squared minus 6y plus 2z is equal to a constant, which is 6. All right, the fact that, and maybe I should use a different color for my comments this time. How about dark green? All right, so this, if you notice here, you have x squared plus y squared plus z squared. That indicates to you, or that should indicate to you, this is a what? Yeah, it's a sphere. So what are these things doing? Well, they basically just move the location of the center, right? And hopefully this will still be positive when you are finished with cleaning. And so you can go to practice test 2 key, which will look like this. And you can also look at this and download this and even print this out if you'd like from that same module. And that's the module entitled test number 2. All right, and so here's your starting point. And what do? Well, you do completing the square. Remember that important process called completing the square. So y squared minus 6y is not exactly a square, right? It's not a complete square. So to complete this square, you add 9 to this, which of course requires you to add 9 on the other side of the equation. And then you have plus 2z, and the whole idea is to take half of this constant and multiply by itself, right? So 2, half of 2 is 1, 1 squared is 1, and negative 6, half of that is negative 3, and negative 3 quantity squared is 9. So you add 9 and 1, which you add on this side. Now this side will be a complete square, which is equal to 16, and this clearly tells you it's a sphere. It's the sphere of radius 4, centered at 0, 3, and negative 1. Remember, these numbers follow a negative sign. So if it happens to be a positive 1, that means in this case, the center has the z coordinate of negative 1. Okay. What's the difference between 1 and 2? Well, if you look at number 2, you have a negative sign between x squared and y squared. And then, of course, the coefficients are different, 1, negative 1, and 9, right? And so of all of these, in all of these, what you have to do is to study the traces. So basically what you're doing is to cut these surfaces at certain specific and particular planes, namely the XY plane, the XZ plane, and the YZ plane. And then try to figure out what the cross section looks like. And those cross sections are called traces. And we've studied this, and so you should be able to know how to do this already. Okay, so number 2, you first let x be equal to 0. That will give you the cross section on the YZ plane. And if this is 0, then you can see the result is 9z squared minus y squared is equal to 9. You can divide everything by 9. This is clearly in hyperbola. This distance is 1. on the z direction, and the y direction is 3. I'm talking about the length of the semi-minor axis and semi-major axis. And so that will give you this hyperbola. Now, the reason this is this way and not this way is because it starts with z square, and then the negative side, negative is followed by y square. Okay, whatever starts this equation, the positive side gives you the coordinate, the intercepts. Okay, and then if y is equal to 0, this will give you the cross section on the xz plane, what you're seeing here. And if y is equal to 0, then you have x squared plus 9z squared is equal to 9. And this is the equation you get, and you will have an ellipse. It's basically 3 here and 1 here, right? And so that's an ellipse because it's connected by a plus sign. If z is equal to 0 here, you have x squared minus y squared is equal to -9, and that's a hyperbola on the xy plane, otherwise known as the plane z is equal to 0. And so if you combine all of these three pictures, you will get, hopefully you practice this many times, so hopefully you will see that the result will look something like this. And I know that some people have a difficult time drawing one picture out of the three, okay? So that's when you need to practice, and that's why we have homework problems, okay? And so hopefully you have had enough practice to be able to draw a picture like this. And the name, of course, the name is important, okay? You should be able to identify these surfaces by name. And since you have an ellipse, ellipse, hyperbola, hyperbola, the answer is an elliptical hyperboloid. And since it's not connected, it is connected, as opposed to, remember that there's a disconnected version like this. This would be called an elliptic hyperboloid of 2 sheets, but here it's connected, so it's an elliptic hyperboloid of 1 sheet. I hope that would make sense. All right. Okay, let's go to number 3. Number 3, what's different? What's the difference between number 3 and the other ones? Well, this time you have z without the squared little number 2. Okay, so z does not get squared, the others do. And that is a classic property for a paraboloid. Okay, and of course you will see that in a moment. But in number 3, if x is equal to 0, you get basically you get, you know, this part, which is saying 9z is equal to y squared. And so hopefully you should be able to draw this parabola on the plane x is equal to 0. And the fact that you divide this by 9 means it's a wide parabola, still opening up upward because it's a positive number. When y is equal to 0, so the middle term goes away, and so you will have z is equal to -x squared, which is an upside down parabola. Okay, so far we have a parabola and a parabola, and therefore the result will be called a paraboloid. The last one, if z is equal to 0, if this term is 0, clearly you can see y is equal to 9x squared. You can solve this for y, and you will see that you will get 2 lines intersecting each other at the origin. Okay, and so if you combine this, and by the way, this happens to be the degenerate case, right? If z is not 0, like for instance, you can try this with z is equal to 1 or -1 or something, you will see an hyperbola normally. The only time you don't see a hyperbola when you cross this surface with a horizontal plane is right at the xy plane when z is equal to 0. So if this is not satisfactory to you, you can try different values of z. Okay, I would suggest like z is equal to 9 or -9 or something and see what happens. Anyway, you will see typically in hyperbola. And again, by this time, you have seen basically just one example of a paraboloid, and that is an hyperboloid. Well, you have a circular hyperboloid, which looks like a cup, but then this is an hyperbolic paraboloid, otherwise known as a saddle. And as soon as you see a parabola opening up and a parabola opening down, the chances are it's almost always an hyperbolic paraboloid. All right, number 4. Feel free to pause this at any moment and you know, get a break or get something to drink or whatever. Okay, number 4. Number 4, the problem here is of this form, x is squared, y is squared, z is squared, everything is positive. So it's like the sphere, number 1, except the constants or coefficients are different, especially in this case, z has a different coefficient. So you can do cross sections like we did before. When x is equal to 0, you have this ellipse. If y is 0, you also have an ellipse. These are rather flat ellipses. And then when z is equal to 0, you actually get a circle, which is a special type of an ellipse. Combining all this, you will get an ellipsoid. Now, an ellipsoid is the easiest one to detect because all of these are positive and the numbers are different. If the numbers are all the same, then you have a circle, right? And so this is like a flat ellipsoid. It's sort of like you know, 2 hamburger buns put together or something. Or like an UFO or something, right? Okay, number 5. Something very special about number 5 is that one variable is missing. And if that happens, as you remember, it goes, you draw this on a plane, and then you extend it in the direction of the missing variable. You remember that? So if y is missing, whatever you draw on the plane, y is equal to 0 is your cross section. In this case, it's an ellipse. And then you drag every point of the ellipse in the y direction, and you will have an elliptic cylinder. Okay, this one sort of looks like a pillow, except it's infinitely long. All right, numbers 6 and 7, actually 6, 7, and 8, they all have to do with these different coordinate systems in 3D that you learned. Specifically, I'm talking about cylindrical coordinates and the spherical coordinates. These two systems, along with the one that you were already familiar with, which is the Cartesian coordinate system, otherwise known as the rectangular coordinate system, you should be able to switch from one to another, okay, to one to the other two. And you can memorize the formulas. I have you know, many formulas to go from cylindrical to Cartesian or Cartesian to spherical or vice versa. But what I really want you to do is to understand what these things, what these variables mean, and for you to be able to sketch so you can convert without being dependent on those formulas. Okay, so for instance, when the Cartesian coordinates are 3, 3, 3, go ahead and try to draw a picture of it. Oh, I forgot. I guess we should go back to number 6. In a spherical coordinate system, what is rho is equal to 3? Rho is the distance from the origin, and phi is the distance. Remember, phi is the angle from the positive z-axis, right? So with that, if you want the phi to be, you know, of course, the minimum the phi has to be, can be, is 0. So if phi is less than or equal to pi over 3, we're talking about this region. And so the answers for number 6 are as follows. Rho is equal to 3 is a sphere of radius 3. If phi has to be less than or equal to pi over 3, then you get this upward cone together with all the points inside. Okay, so, and of course, this goes infinitely long. That's the answer for the second part of number 6. And in number 7, in cylindrical coordinates, r is equal to 2. I hope you can see that this has to be a vertical circular cylinder. And then theta is equal to pi. That's actually on the other side of the x-axis, right? So the it's sort of like a half of this plane. It's a half plane where a theta is equal to pi. So it's kind of going, you know, from this is where theta is equal to 0. And so you go over 180 degrees. And so the first one is a vertical cylinder, and the second one is a vertical half plane. All right, going back to 8, you have 3 points, and the answers. All right, so let's see, 3, 3, 3 is given. So you can draw 3 here, and then 3 here, and then go up by 3. Okay, so this is the point 3, 3, 3. And I think it's easier to drop this down to this point 3, 3, 0. And that answers your question. How far is this point from the origin? And the answer is 3 square root of 2. Of course, you can always do square root of x squared plus y squared, but geometrically, it's obvious. Also, I hope it's obvious that theta is pi over 4 because 3, 3 will give you an angle whose tangent is equal to 1. And of course, its picture, the picture makes it clear that the theta has to be pi over 4. And then the z value, of course, this has to be equal to this z value. So that's it. Then in order to go to the spherical coordinate system, of course, you know that this point is how far from the origin. You take this calculation, square root of 3 squared plus 3 squared plus 3 squared, and that is your rho. And the theta, the second coordinate here, has to be equal to this theta, because that's the same theta. And then the last one, you have to figure out what this rho is, okay? I mean, sorry, the phi. But here's this picture. Maybe I should explain this. This is the picture. This is the triangle I should focus on. And that triangle is the right triangle. Okay, so the bottom here looks like it's 3 square root of 2. And this is 3. And so this is actually not the right answer, is it? Is it? I need to fix this problem here. Hold on a second. Yeah, so you cannot be too careful in these things. Remember, this is a right triangle, and this is the triangle that I'm showing here. The length r here is the square root of, what did I say? It's 3 times the square root of 2, okay? And then height is just 3, right? And remember, the theta is this angle here, but that's the same as this angle here because those are the alternate interior angles. So in this case, phi is the angle whose tangent is 3 square root of 2 over 3. Okay, well, that's the same thing as the square root of 2. So this is the inverse tangent of the square root of 2. Okay, and so that is the answer to this question. Oh, sorry for making a mistake here. By the time you see this, I'm sure it's fixed, but the answer is inverse tangent of the square root of 2. Oh, that's a tricky one. All right, in the second example, what is given here? In the second example, you are given this, the middle one, and so this is given, and so what you draw is you go in the direction, well, first, r is equal to 1, right? And then since theta is negative pi over 2, you actually go in this direction by 90 degrees. And then this is 1 here. That's actually y is equal to negative 1 here, right? And then the z is 2. Okay, so this is 1. This is 1. And the length is, the height is 2. Okay, so that's the picture you have. And so the, of course, the, what is this? The x coordinate is 0 just because you went theta is negative pi over 2. When theta is negative pi over 2 or positive pi over 2, of course, your x coordinate will be 0. And then the second coordinate is negative pi over 2, which is, of course, like I said, it's this way. And then what's the y? Well, the y value, you know, this r is equal to 1. So it's telling you to go start at the origin and go in this direction 1 unit, which will give you negative 1 as your y coordinate. Again, you can do, you know, x is equal to r cosine theta, y is r sine theta, and those will give you these numbers, but the picture makes it clear. Z is the same z here, so no problem here. Theta and this theta are the same, right? So you don't have to worry about that part. But what is the rho, the value of rho? Well, if this is 1 and if this is 2, this is rho, and that's the square root of 1 squared plus 2 squared, which is the square root of 5. Right? Theta is given already, and as I said before, the angle here is the angle here, and that's your phi. And this phi is the angle whose tangent is 1 over 2. And so that is the answer for that phi. All right, finally, you have, let's see, you are given this one, right? Let's see if you were given that. Yeah, 6, 0, pi over 2 in spherical coordinates. So that means you go in whatever direction you go 6 units. It doesn't really help you to draw this yet, right? This is 0. Theta is equal to 0. So that means it's on this positive x-axis, right? And then this one, phi is pi over 2, which actually means you go 90 degrees from the positive z-axis, and that's going to put you right into the xy plane. This tells you that the point is on the xy plane. And it's 6 units away from the origin, and the theta is 0. So this has to be this point, okay? This point is called 6, 0, 0 in Cartesian coordinates. And the r is, of course, 6. Theta is, of course, theta 0. And then the z value, since it's on the xy plane, is equal to 0. So hopefully you have seen that I have I have not used any of these formulas. I want you to understand the concepts of things like phi and theta and rho and r in relation to x, y, and z. And if you can picture these points, then you should be able to convert between the coordinate systems. All right, I will stop this at this point, and then when we come back, we'll go to the second part of this.